This is our CNC machine. We built it with fabricated steel as opposed to extruded aluminum products. I'm going to walk you through how we did it and ended up with what you see in front of you. So the construction on the machine was all 2.5 inch box steel, 4 inch box steel, a bunch of plate cuts, and then just wide flange. So the X-axis, the long axis of the machine, is all 6 inch wide flange, quarter wall. And then the big beam up top, I think, is just a 9 inch deep I-beam. It was just a piece of scrap I had lying around that was still relatively straight. And then just a bunch of odds and ends. So there's probably 1,000, 1,200 pounds just in steel in this machine. When I was designing the table, I drew up everything in CAD and then modeled the whole thing in like a 3D modeling software. The reason I did that was just to make sure that all the parts were gonna fit together well. As you can see, they all kind of, straddle each other and sort of conform to very specific fitments. So I wanted to model it all up and just make sure that it was all gonna go together properly. You can see the rigging points there on the end, so we can pick it up. It's got 4 rigging points, 4 in total, 1 on each corner. And that is sort of the only way we can move it. Definitely not picking it up and putting it in the back of a truck. Fortunately, it doesn't move around very much, and honestly, building a CNC machine under the pretense of portability doesn't exactly make a lot of sense. I'd rather it be a heavy piece of nasty iron in the corner that never moves than something that's lightweight and flimsy and can pick up. I don't really see the point of that. So for our purposes, this is definitely the way to go. The machine uses NEMA 34 stepper motors. It has 25 millimeter diameter 5 mil pitch screws for the Y and the Z axis. It uses 10 millimeter pitch screws down the X axis, which I'll explain later. The bearings, screws, and rails were all purchased as a kit. They were just bought as a package in the various lengths that I needed to make the machine an effective 4x8 inch working surface. All the rails and screws are Chinese made. They're a small fraction of the cost of good screws, and they perform half decently, so I'm not going to complain. I went with screws on this machine just because I thought they would be more precise. It also seemed like an easier installation as opposed to trying to do a rack assembly and carriage mounting the motors or something along those lines. So this just made a bit more sense to me. Also, I assumed it would probably run a little bit more smooth and accurately as opposed to a rack and gear drive system, which will have a bit of backlash and just in general probably not operate quite as fluidly. So those were my assumptions. I'm happy with the screws. All the motors on this machine are NEMA 34 1600 ounce stepper motors. They are a open loop motor, which means they don't have encoders. So they're not ideal, but they are the most cost effective option. They seem to run pretty decently. The things I don't like about them is they generate quite a bit of heat. They have quite a bit of low speed resonance. They seem to hum and put a lot of vibration in the machine when they're at low speeds. Something to consider. They also don't have very linear power curves, so they drastically lose power at high RPMs. Sometimes when it's really spinning, you'll hear it make kind of a funky noise and sort of trip over itself. That's just because they're not good at high RPMs. So here's the back of the machine. We have our 2 NEMA 34 1600 ounce driver motors for the X-axis. So this is the slave, the other one's the master. For the most part, they work pretty good. We have had a few issues where one motor will trip or stall, as they tend to do when they're either outside of their temperature range or RPM range or load capacity, any number of reasons. But when they do trip up, they go out of sync temporarily, and it will cause a racking situation of the gantry, which basically means that you will take the gantry out of square. To some degree or another, we've had it happen pretty bad. I did eventually install some limit switches on the gantry that will register a racking condition, just so the machine doesn't continue to attempt to operate if the gantry has been racked. I think if I built another machine or modified this one, I would use servos or at least a closed loop stepper, at least in any kind of scenario where two motors have to operate in perfect unison, just to avoid that issue. And most likely I will change these motors out. So these are the control boxes. There's 3 of them for the machine. This one is sort of our AC box, so it has power coming in on the sides, just with C14 electrical connectors. Those run into breaker/reset switches, so that's how we actually turn the machine on and off. Those go into some distribution blocks, send the power around. It sends some AC power into the motor power supplies. There's a 24 volt power supply right there, which powers the electrical fans and some of the other DC equipment. There's a couple power relays there. They're wired to the breakout board, so the computer program Mach 3 can initiate 120 volt circuits, so it can power the router, it could power any other accessory we wanted it to power. So this is our AC box, feeding 120 volt power to our motor drivers. So these are not drivers, I should say power supplies. I think they convert to 60 volt DC for the motors. They need to produce about 6 amps. These are 1600 ounce motors. I think they take in the neighborhood of 6 or 7 amps. So these are the drivers. We have 4 of them, the ZYX and X slave, because obviously there's 2 on the X axis. They send DC power to the drivers here. So there's 4 of them again. These are what send the motor signals out, do the micro stepping as well. So they have DC power connections from the power supplies. They have power out to the motors, and they have their signal connection down to the breakout board, which is here. So this is just a standard breakout board. I believe it came with the motors. They were a package, so the motors, the power supplies, and the drivers all came together. So here's a breakout board. This is what all the electrical motor signals are connected to. Some of the accessory power signals are connected to. The end-stop switches and E-stop switches are also wired into here. So that we have connected to our smooth stepper. So this is an upgrade we did after the fact. Highly recommended if you're building a machine. Buy one of these right off the bat. They're only about 250 bucks. They're worth every penny. We were able to run the machine so much faster, and it seems to just be smoother and more stable, and well worth it. So they have them available, I believe, with Ethernet connections, which is what we're using, back to the PC, and USB connections. All these boxes are air cooled. The power supply box can get quite warm. This got a big DC fan there that blows air through and right out the top. All 3 of them have this. I put little filters on too, just to try and keep the dust out of the boxes, because as you can imagine, it gets pretty dusty. This whole machine is designed around the concept of installing the rails and the screws inside the wide flange. The idea there was that they're just sort of out of the way and protected. I could also install machine bellows over this open surface and kind of protect them from dust. I have not done that yet. Did present some complications as far as nesting everything inside a 6-inch flange. Like, the tolerances are pretty tight. It's fine, they're all machined parts, but I probably was able to pull this off with a little bit more luck than I would have liked. We did have to go and trim some parts, but it all went together and it operates pretty nicely. Serviceability is a bit of a challenge. We did have to service one of the screws and had to cut a chunk out of the top flange just to get it out. But other than that, I'm pretty happy with the design. There was a bit of a resonance problem because ultimately the rails were just mounted on this lower 3/16" flange. So they didn't have a ton of support. So we added some welded bar to the bottom. I think that's just 3/4 inch solid bar, just welded underneath, just to add a bit more material. Also added some granite epoxy on the inside of the wide flange on both sides. So all that is epoxy mixed with sand, and apparently it has really good properties for killing resonance and relatively lightweight, I guess, for its volume. All we did was just turn the whole frame on its side when it was being fabricated, pour that in, and it goes a long way to killing the resonance. Steel tends to ring, even heavy steel like this, but it really takes the vibrations out of the steel, which is great considering this lower flange carries so much weight. This big ass gantry is, my best guess is around 400, maybe 450 pounds. That was sort of by design. Any machine I'm familiar with capitalizes on mass to sort of reduce resonance, and it's just less likely to deflect. If you imagine the full weight of that gantry basically holding the router in place, it's much less likely to lift or deflect under just basic tool loads. I'm quite confident I could stand on the rotor and that thing would move around as if I wasn't there. I think that's a major advantage over some of the aluminum built machines. I wanted this machine to be able to mill metal products. Here is the ZAxis. It is a fabricated steel component, so basically it was a bunch of plate cuts that were all welded together. I used tabs in the plate cuts just so everything would align perfectly. Once it was welded, we threw it on the mill. It was a small enough piece so we could throw it on a mill table and just verify the flatness of it. The rails were then mounted directly to the back plate. Those rails are the same 20 mil rails that we used on the X and Y axis, and then it uses a smaller diameter. I think that's a 16 millimeter 5 mil pitch drive screw. Works pretty good. The snout and rotor mount on that ZAxis is probably 80 pounds, and that screw is able to lift that thing up no problem. So that seems to work pretty good. This is our dust collection assembly that I whipped up. Just aluminum plate. It needs some fine tuning. I have 2 different Velcro skirts that we can put on it with the brushes. Just different heights depending on what kind of operation we're doing. It just lifts into place. There we go. So it just sort of locks into the back, slides up and pins in. The whole router is mounted on a pedestal, so you can kind of see a fabricated clamp assembly there. So that actually is adjustable. One of the things I would recommend is making your router, it's very unlikely that you'll get it perfectly in the plane of the Z-axis. So we have it on this mount where you can actually correct it this way or this way, as well as this way or this way. So we can plumb it up for face milling operations. Just because, like anything, you know, this is fabricated steel. Depending on how you install it, you may find it challenging to get that thing perfectly parallel with the machine. If you don't want to buy a proper spindle right away, I will 100% recommend these Bosch routers. We've been running it the entire time we've had this machine. It is indestructible. It has never stopped, failed, sparked, overheated. We've crashed it, run big face mill jobs with it. You name it. It's got 500 plus hours into it. We've done jobs where we run it, 7 hours straight. Again, no complaints from this router. Lots of power. For the 250 bucks, if you're not willing to invest in a water-cooled AC spindle with a VFD right away, just buy one of these. They're incredible. You will not be disappointed. Because this is a fabricated steel table, the number one challenge and the number one advantage to using an extruded aluminum product is sort of straightness. So when you put the whole machine together with aluminum extrusion, the members are fairly straight, so you don't have to worry too much about the linearity. So fabricated steel is a little different. no matter how hard you try, when you're fabricating, I had this whole thing clamped down to a stronghold fabrication table, which is very rigid and very sturdy and very flat. Nonetheless, when you start welding the steel and putting heat into it, it all twists and warps to a certain extent, and that will have to be corrected for in your rail systems. So that's what we did. So at the end of the day, it doesn't really matter if the machine itself isn't perfectly straight or linear when it comes off the fab table. You can correct this. We just used machine shims, which exist for a variety of reasons, but they're basically available in nominations from 1/1000th of an inch up to, I think, 75/1000th of an inch. In the kit I bought, they just came in a package with a selection of everything. So when we started mounting the rails, we just took care to shim them. We used a datum point dial deflection gauge to run the gantry along the rails as they were installed, and we sort of shimmed them up or down, whatever we needed to do to get them nice and straight. The datum we used was a plate out of the fab table. The plates are 1/2 inch thick. They are precision ground, I think, to 4/1000th of an inch over their 4-foot span. So that was the data point that we used to dial in the machine. So we should be pretty close to that as far as our linearity. So the screws down here are currently 10mm pitch screws. As I had mentioned, they were initially 5mm pitch screws. The reason for the change out was ultimately a failure. We had a problem with one of the ball nuts, but I believe it was as a result of a design flaw in the machine. So because these screws are so long, they are 2,900 millimeters long. They have quite a long unsupported span, so if the gantry's on either end of its travel, you're looking at, 7 feet of unsupported screw. And the metal's fairly hard, but it's not hard enough, so I mean, it just sags a little. The problem being that when it's also being turned, that sag sort of has a jump rope effect, and it starts throwing the unsupported weight of the screw around. We were finding with the 5mm pitch screws, because those stepper motors had to turn in essence twice as fast to achieve the same speed as this 10mm screw, that it would really throw those screws around. So it put quite a bit of vibration in the machine. I think it's what destroyed the ball nut. It's just that vibration over time. That being said, we still got 500 hours out of them, so it wasn't too bad. The 10mm pitch screws are much better. The motor spins slower, there's less vibration, the whole machine is capable of much higher travel speeds, which was another thing to consider. And if I designed it again, I would probably use 10mm pitch screws everywhere. The 5mm pitch just seem a bit unnecessary. With the micro stepping in the motors, you just don't need the accuracy and resolution you get out of a 5mm screw. So I would go with the 10mm. So down on the gantry block here, this is one of those limit switches right there that I was telling you about. So if the gantry racks, they actually ride along the rails. There's one on either side of the gantry, and if the gantry racks at all, it will trip one of those 2 limit switches and throw the machine into an error state. We have limit switches all over this machine. So this is the switch for the end of the Y-axis travel. There's one on each end of that. There's limit switches on the Z-axis top and bottom, and then the length limit switches on the X-axis, as well as the racking ones. They do come in handy. Even if you're good on the machine, things go wrong, or you miscalculate your work area, or the machine runs away from you, something will happen. They've definitely saved us a few times. I would absolutely put them in. The machine can do a lot of damage to itself. It can be deceiving. It doesn't maybe seem like the case, but trust me, it can. So it's worth the $2 a piece, or whatever these things are worth. Just buy them and put them on. Feature are the EStops. So I put 3 on this machine. There's one on the Z-axis, there's one on the side of the gantry, and there's one on about a 30-foot cable that we can sort of bring wherever we need to be. We use them a lot. There is a lot that can go wrong very quickly. It's nothing worse than tripping over yourself trying to find a machine stop button. So we just put them everywhere, especially this one on the Z-axis is pretty convenient, because you'll find yourself around the tool a lot, either holding pieces down or keeping an eye on things or whatever. It's nice to have one right there. The floater's good too. Sometimes when we're running lighter milling jobs and we just don't want to be standing right over the machine the whole time, we just bring the floater over to wherever else we're working, and then at least there's still a stop nearby. So another thing that for the $10 a piece or whatever they're worth, just put them on everywhere. I really enjoyed building this machine. I learned a ton about how machines work and just machining theory, which I think is invaluable, especially when you're going to start using a machine. So there's a huge advantage there. I put a lot of thought into it prior to ever even purchasing a piece of steel. I knew that I wanted to use it commercially and I needed it to perform as such, and thus far it has 500-600 hours on it, more or less problem free, other than some fine tuning here and there. I would build another one like this. I definitely see the advantage to just simplifying and using aluminum rail or as many prefabbed components. You can buy pre-assembled ZAxis and stuff like that, and I understand the appeal to that. This was a bit to bite off. Holy good God, it was a lot of work. I probably spent 6 months putting it together and then another 3 months refining it. I don't know that I saved myself any money if I consider my time worth anything. So there you go. I hope you found this helpful. This is a bit of a different kind of build. Hopefully it gave you some ideas. If you have any questions, feel free to ask me. I would be happy to give as much help as I possibly can. Other than that, good luck with your build if you're looking at doing something similar. And thanks for watching.